Exercise of the chapter Magnetic Materials. Question 1. Answer the following questions regarding Earth's magnetism. A vector needs three quantities for its specification. Name the three independent quantities conventionally used to specify Earth's magnetic field. So there are three quantities: inclination, declination, and horizontal component of Earth's magnetic field. Part B, the angle of dip at a location in southern India is about 18 degree. Would you expect a greater or smaller dip angle in Britain? Britain is in northern hemisphere. So when you move from equator to poles, the angle of dip increases. Therefore, we expect a greater dip angle in Britain. But see, if you made a map of magnetic field lines at Melbourne in Australia, would the lines seem to go into the ground or come out of the ground? Australia is in the southern hemisphere. Therefore, the Earth magnet has its north pole close to the south pole of Earth. So, as it is north pole at the geographical south, the magnetic field lines will come out of the ground. Part D. In which direction would a compass free to move in the vertical plane point to if located right on the geomagnetic north or south pole? At the magnetic poles, there is no horizontal component of Earth magnetic field. Only vertical component is there. If you place the needle right over the magnetic poles, as there is no horizontal component there, it can have in any direction. Okay, there is no particular direction. It can align or it can orient. Whatever direction you keep it there, it remains in the same direction. Part E, the Earth's field is claimed roughly approximates the field due to a dipole of magnetic moment 8 into 10 power 22 joule per Tesla located at its center. Check the order of magnitude of this number in some way. So here, magnetic moment is given. Radius of Earth is 6.4 into 10 power 6 meter. So magnetic field strength. Okay, if you consider the magnet, then almost the equator part when you take, you can calculate the magnetic field at the equatorial plane of a magnetic dipole. And its formula is B is equal to mu naught by 4 pi m by r cube. Okay, so substitute the values, you will get the value of B, and that will be the magnitude of the magnetic field at the equator. Then next, part F, geologists claim that besides the main magnetic north-south poles, there are several local poles on the Earth's surface oriented in different directions. How is such a thing possible at all? We know that there are a lot of mineral deposits over the Earth, and many of those minerals are magnetic materials, like deposits of iron. And those magnetic mineral deposits are already magnetized. So, due to the huge deposit of magnetized material, we can assume the presence of a local pole at that region. This is the reason there are several local poles on Earth's surface. Now, next, question 2 is not required for you. Question 3. A short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 power minus 2 joule. What is the magnitude of magnetic moment of the magnet? We have the equation. Torque is equal to mb sine theta. Torque is equal to mb sine theta. And the values of B, T, torque, theta, etc. are given. So you can calculate the value of M. M is equal to torque upon B sine theta. Substituting the values, you get the answer. Question 4. A short bar magnetic moment M is equal to 0.32 joule per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar is free to rotate in the plane of the field, which orientation would correspond to its stable and unstable equilibrium? At stable equilibrium, magnetic moment and magnetic field are parallel, and at the unstable equilibrium, these two quantities are anti-parallel. Then, what is the potential energy of the magnet in each case? In case A, you can calculate the potential energy U is equal to MP cos 0, because angle is 0, it is minus MP cos 0. Cos 0 is 1, so you will get the equation minus MP. At stable equilibrium, potential energy is negative. And in case B, U is equal to minus MP cos 180. They are anti-parallel. Cos 180 is minus 1. So you will get a plus MP. Substituting the values, you get the answer. Question 5. A closely wound solenoid, 800 turns and area of cross-section 2.5 into 10 power minus 4 meter square, carries a current of 3 ampere. Explain the sense in which the solenoid acts like a bar magnet. What is its associated magnetic moment? So you need to explain how a solenoid becomes a bar magnet in the sense of magnetic field. Each turn produces magnetic field and all the turns are having current in the same direction. And all these fields are combined, superposed, so that you get a resultant magnetic field similar to bar magnet. So you need to explain that part. Then for the numerical part, what is the associated magnetic moment? Magnetic moment M is equal to n number of turns are there. IA is the equation for magnetic moment. All those quantities are given. You can find the value of magnetic moment. Then question 6. If the solenoid of the previous question is free to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied, that means this solenoid having magnetic moment, it's a magnetic dipole, it is placed in an external magnetic field. What is the magnitude of torque on the solenoid when its axis make at an angle 30 degree with the direction of applied field? So you need to calculate the torque. Again, formula for torque is equal to MP sine theta. Value of M you get from the previous question, so that you get the answer. Then question 7. A bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of uniform magnetic field of 0.22 Tesla. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? First case normal to the field direction, and second case opposite to the field direction. So here, the first part it is given, the magnetic moment lies aligned with the uniform magnetic field. That means theta 1 is equal to 0. Now, two cases are given. In case A, there, case 1, the bar magnet is turned normal to the field direction. That means in case 1 theta 2 is equal to 90 degree. Theta 2 is equal to 90 degree. Therefore, work done formula, we can use work done W is equal to MB into cos theta 1 minus cos theta 2. Theta 1 minus theta 2. Now cos 90 is 0, cos 0 is 1. So you will get the answer MB. Substitute the values of M and B, you will get the answer. In second case, value of theta 2 equal to 180 degree. Theta 2 is equal to 180 degree. Therefore, W is equal to MB into cos theta 1 minus cos theta 2. And cos 180 is negative 1. So you will get the answer 2MB. Substituting, you get the answer. Now for part B, what is the torque on the magnet in case 1 and 2? Torque formula, we know torque is equal to MB sin theta, where theta is the angle of rotation. In the first case, in case 1, angular rotation is 90 degree. Therefore, torque is equal to MB sin 90. Sin 90 is 1. Therefore, you will get MB. Torque is equal to MB. In second case, angular rotation is 180 degree. So, torque is equal to MB sin 180. Sin 180 is 0. So, torque is 0. Now, question 8. A closely wound solenoid 2010s and area cross section 1.6 into 10 power minus 4 meter square carrying current 4 ampere is suspended through its center, allowing it to turn in a horizontal plane. What is a magnetic moment? Again, we have same formula for magnetic moment. M is equal to NIA. Then, what is the force and torque on the solenoid if a uniform horizontal magnetic field of 7.5 into 10 power minus 2 Tesla is set up at an angle of 30 degree with the axis of rotation? So what is the force? Force will be, there will be equal and opposite forces. So force is equal to 0 and torque is equal to MB sin theta. Torque is equal to MB sin theta. Substitute and find the answer. Question 9. A circular coil of 16 turns and radius 10 centimeter carrying a current of 0.75 ampere rests with its plane normal to an external field of magnitude 5 into 10 power minus 2 Tesla. The coil is free to turn about an axis in its plane perpendicular to the field direction. When the coil is turned slightly and released, it oscillates about its stable equilibrium with a frequency of 2 in 2 per second. What is the moment of inertia of the coil about its axis of rotation? We have frequency nu is equal to 1 by 2 pi into under root mp by I, where I is the moment of inertia. I is the moment of inertia, so which we can write as Im to avoid confusion. Now here, square the equation and cross multiply. You will get moment of inertia Im is equal to mp upon 4 pi square nu square. Here we need to find magnetic moment M. Magnetic moment M is equal to NIA, where I is the current. NIA. Again, area is not given, but radius is given. Therefore, NI into pi r square will give magnetic moment. So substitute the value of magnetic moment in the formula for moment of inertia Im. Then simplify. So we can find the answer. Now question 10. A magnetic needle free to rotate in a vertical plane parallel to the magnetic meridian has its north tip pointing down at 22 degree with the horizontal. So angle between horizontal component of earth magnetic field and its total magnetic field is the angle of dip is 22 degree. The horizontal component of earth magnetic field at the place is known to be 0.35 Gauss. Determine the magnitude of the earth's magnetic field at the place. We have the formula. The horizontal component of earth magnetic field BH is equal to B cos I, where I is the angle of dip 22 degree. From there, B is equal to BH upon cos I, cos 22. So substitute the values, you get the answer. Then question 11. At a certain location in Africa, a compass points 12 degrees west of the geographic north. The north tip of the magnetic needle of a dip circle placed in the plane of the magnetic meridian points 60 degree above the horizontal. 60 degree above the horizontal. The horizontal component of Earth's magnetic field is measured to be 0.16 Gauss. Specify the direction and magnitude of Earth's magnetic field. Again, we have to use the same formula. B is equal to BH upon cos I. Now, the dip circle shows the total magnetic field. It makes an angle 60 degree with the horizontal. Therefore, angle of dip I is equal to 60 degree. And you can substitute the values. You get the answer. Then next question 12. A short bar magnet has a magnetic moment 0.48 Joule per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance of 10 centimeter. You have to take a distance r is equal to 10 centimeter from the center of the magnet on the axis and the equatorial line of the magnet. So B axial is equal to mu naught by 4 pi 2m by r cube, and B equatorial is equal to B axial by 2, or its formula is mu naught by 4 pi m by r cube. So you get the answer. Now next question 13. A short bar magnet placed in a horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 centimeter from the center of the magnet. The Earth's magnetic field at the place is 0.36 Gauss and angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point, that is 14 centimeter from the center of the magnet? Okay. So here, first we have to take the north-south directions. North-south directions. Then we have east, west. Now the magnet is placed along the north-south direction. The magnet is placed like this. The bar magnet is placed in this way. Now the question says that the null point is obtained here. The null point. What is the direction of Earth magnetic field there? Earth magnetic field, we know Earth magnetic field is directed from geographical south to geographical north, because at the south pole of Earth, magnetic north is there. So Earth magnetic field is always from geographical south to geographical north. So the direction of Earth magnetic field. So here we can have BH. Here BH is equal to B because angle of dip is given 0 there. Now first we have to decide which pole is here. You are getting null point here. This is the null point. As it is null point means there no magnetic field. Which means there is a magnetic field there cancelling this BH. So which pole must be there for that purpose? We know south pole must be there. So that B axial is acting towards the south pole, B axis. And total distance it is given 14 centimeter from there, from the center of the magnet. The total distance is given 14 centimeter. So this is R is equal to 14 centimeter. So from that we can conclude there at the null point BA, B axial is towards south pole and BH is towards north. So they mutually cancel each other. Therefore, we can write here we have BH is equal to B axial. That is why we get null point there. Now the question is that for the same 14 centimeter, what will be the value of magnetic field along the horizontal axis? So we take the same 14 centimeter here. So the distance is 14 centimeter from the center of the magnet. 14 centimeter. So horizontal distance we have same 14 centimeter. Then at this point, what is the magnetic field? That is what we need to calculate. And here again you can see BH is in the same direction. Okay, BH is at that point also BH is towards north. So what is the direction of Earth magnetic field there? Earth magnetic field we know. Okay, Earth magnetic field BH is towards north. And what about the direction of the magnetic field produced by bar magnet? Bar magnetic field is like this from north pole to south pole. This is north pole of the magnet. It is from north pole to south pole like this it will go. That means you can see at this point magnetic field due to the bar magnet is also in the direction of BH like this, and it is the equatorial plane of the bar magnet, therefore we can say it is B equatorial. So then what is the total magnetic field at this point? The total magnetic field B total is equal to, as both Earth magnetic field and B equatorial are in the same direction, we can write it is BH plus B equatorial because both are in the same direction. Now that is equal to BH plus B equatorial means it is B axial by 2. That is equal to BH plus, now B axial by 2, and B axial we got already. B axial is equal to BH. So you will get BH by 2. Therefore, B total is equal to 3BH upon. So substitute the value of BH, you get the answer. Now, next. If the bar magnet in the previous exercise is turned around by 180 degree, where will the new null points be located? So in this case, again, we have to go for the diagram. So we have north, south, east, west directions. Now we can have a north, south, east, west. The bar magnet is placed there. Now it is rotated through 180 degrees. So here you will get north pole and here south pole. And the same BH is acting from north to south to north again, BH. Now here you take a point at the axis. Now north pole is there. As north pole is there, then you can see the difference. The B axial is also now directed upward. B axial is also directed upward. So then what happens? This is B axial. As it is north pole, it is emerging out. Both BH and B axial are in the same direction. So there is no possibility of getting a null point at the axis. So now what is the next option? Think about the equatorial plane. At the equatorial plane, again you can see BH is acting towards north. So we have BH from geographic south to geographic north. Now what is the direction of this magnetic field of the bar magnet? We have to see there. Direction of the bar magnetic field of the bar magnet is from north to south, like this. Therefore, the possibility you can see there, now B equatorial is acting towards here. B equatorial. And for a given distance, we can say R1. For a distance R1, we can say BH is equal to B equatorial, so that this point becomes a null point. That point becomes a null point. So null point is obtained on the equatorial plane of the bar magnet. Okay. So that must be got the idea now. So now we can say BH is equal to B equatorial for the distance R1 to get the null point. That is BH is equal to, we have mu naught by 4 pi m by R1 cube. You will get. And that is equal to, again we know V equatorial is B axial upon 2. And the value of B axial we have mu naught by 4 pi it will be there. If we think about the previous question, in the previous question we got BH is equal to, because we have the same magnetic field, everything is same. BH is equal to B axial for a distance of 14 centimeter. So B axial is equal to mu naught by 4 pi 2m upon R cube, where R cube is 14 centimeter. Now in the In question number 13, BH is equal to BA. Question number 14, BH is equal to B equatorial. So we can equate these two. When you equate, okay, you will get 1 by R1 cube is equal to 2 by R cube. Remember, R is 14 centimeter. From that, you will get R1 is equal to R divided by 2 raised to 1 by 3. You have to take the cube root so that you get the value of R1. Now, next question 15. A short bar magnet of magnetic moment 5.25 into 10 power minus 2 joule per Tesla is placed with its axis perpendicular to the Earth's magnetic field direction. At one distance from the center of the magnet, the resultant field is inclined at 45 degree with the Earth's field on first case its normal bisector, second case its axis. Magnitude of Earth's magnetic field at the place is given to be 0.42 cos. Ignore the length of the magnet. So again, we have to take Earth magnetic field and north-south directions and all. So now a bar magnet is placed in such a way that it is in the horizontal bisector like this. The bar magnet now placed. Now here, in this case, we have again the Earth total magnetic field BE is acting from south to north. South to north. Now you take this one as south pole and this one as the north pole. And at the equator, the B value of B equatorial is in this direction. The resultant of B equatorial. Now, the resultant of BE and B equatorial makes an angle 45 degree. That is what given in the question. The total magnetic field makes an angle 45 degree there. The B total makes an angle 45 degree. This is also 45 degree. So when you get a resultant of two vectors 45 degree, when those two vectors are equal, which means you will get BE is equal to B equatorial. BE is equal to B equatorial. So you can substitute the value BE is equal, this is for case A. BE is equal to B equatorial value is mu naught by 4 pi m by r cube. You know the value of B, M, etc. So that the value of R you can calculate. Now take case B. In case B, it is placed at its axis. So think about the axis there. So this is the axial line. At the axial line, we have to take a point. Again, B is acting from north, from south to north, B. Now, B axial is normally outward, and the resultant magnetic field makes an angle 45 degree here. Again, this is B total. And you get it 45 degree again, as I mentioned before, when B axial is equal to B, when both the vectors are equal. So you will get BE is equal to B axial is equal to mu naught by 4 pi 2m by r cube. So cross multiply the equation and you can find the value of r for to what distance it happens. Then next Question 18. A long straight horizontal cable carries a current 2.5 ampere in the direction 10 degrees south of west to 10 degree north of east. Okay. The magnetic meridian of the place happens to be 10 degree west of the geographic meridian. The magnetic the Earth's magnetic field at the location is 0.33 gauss and angle of dip is 0. Locate the lines of neutral points. Okay. So neutral point where the magnetic fields are mutually cancelled, we need to calculate. Again, we have to go for the diagram. So here we have geographical south, north, east, west. Now the question says that there is a cable carrying current. The cable is 10 degree like this. It is 10 degree south of west and north of east. This angle 10 degree. It carries current I. Now magnetic meridian, again we have to see. Magnetic meridian makes 10 degree west of geographic meridian. The same way. So this is magnetic south pole and magnetic north pole making an angle 10 degree there. Now you can see where are the neutral points. Here you can see BH will be in this direction along the magnetic meridian. So we have BH. Now BH is one of the magnetic fields. The second magnetic field is the magnetic field produced by the cable. Magnetic field produced by the cable, we have BC is equal to mu naught by 4 pi 2I by R. Mu naught by 4 pi 2I by R. This is the second magnetic field. Then you can see there apply right hand thumb rule. When you apply right hand thumb rule, you can see above the cable, the magnetic field is towards southern part, above the cable, while BH is towards northern part. So at a particular height, the BH towards geographical north and BC towards geographical south become equal and opposite and they mutually cancel each other. It happens above the table when you above the cable when you apply the right hand thumb rule. So that we can say BC is equal to BH. BC is equal to BH. So is equal to mu naught by 4 pi 2I by R. Substitute the values, find the value of R. So you will get a null point at a height R from the table above it. That will be the answer. Now, question 19. A telephone cable at a place has 4 long straight horizontal wires carrying a current of 1 ampere in the same direction east to west. The Earth magnetic field at a place is 0.39 gauss and the angle of dip is 35 degree. The magnetic declination is nearly 0. What are the resultant magnetic fields at a point 4 centimeter below the cable? So we have a cable and the cable is carrying current from east to west direction. Current is from east to west, direction. Now, naturally, the BH, horizontal component of Earth magnetic field, BH, is from geographic south pole to north pole. BH is from geographic south to north. So now you can see below the cable, apply right hand thumb rule, below the cable, the magnetic field is opposite to BH. Because thumb should be in the direction of current. Below the cable, you can see VH and magnetic field due to the cable are in the opposite direction. Now here, the first what we have to do, total magnetic field is given. You have to find the value of BH. BH is equal to B cosine, and BV also you have to find out. BV is equal to B sin I. So find the value of VH and VV. After getting VH and VV, you can calculate the magnetic field produced by the cables. So magnetic field due to a wire, current carrying wire is 4 pi V naught by 4 pi into 2I by R into 4, because we have 4 cables are there. So you get the value of BC. And below the cable, already I mentioned BC and BH are in the opposite direction. So find the value of resultant BH, which we can take as BH dash. BH dash is equal to BH minus BC. Because again, below the cable, BH and BC are in the opposite direction. So here you get the value of BH dash. Then you can find the Earth's total magnetic field there. Earth total magnetic field B is equal to under root horizontal component BH dash square plus BV square. BV will be same. There is no change for BV. So you will get the total magnetic field below the cable. And for getting its direction, you have to take tan theta. Tan theta is equal to BV upon BH dash. From that, you can find the value of theta. So you get the direction. And remember, in case the question is for above the cable, so what is the change you have to make? Below the cable, BH and BC are in the opposite direction. So we took the difference to get the resultant horizontal component BH dash. If it is above the cable, for getting BH dash, you have to take BH plus BC, because above the cable, BH and BC are in the same direction. Now, come to question 20. A compass needle free to turn in a horizontal plane is placed at the center of the circular coil of 30 turns and radius 12 centimeter. The coil is in a vertical plane making an angle of 45 degree with the magnetic meridian. When the current in the coil is 0.35 ampere, the needle points west to east. Determine the horizontal component of Earth's magnetic field at the location. So here, once again, we have to take the directions. So we have north, south, east, west. Now, as we used to discuss, BH is acting towards the upward. BH, horizontal component of Earth magnetic field. Now the coil is placed. The coil is placed in such a way that its plane make an angle 45 degree. like this, the coil is placed. Plane, make an angle 45 degree. Now the plane of the coil makes an angle 45 degree like this. The plane 45 degree. This is the plane of the coil. Plane of the coil makes an angle 45 degree. So that we can see the magnetic field of the coil from the center acting like this normally outward. So this is the magnetic field of the coil BC. Now a compass needle is placed there, and that compass needle has a direction west to east. So the needle, compass needle placed here. This is the needle west to east like this compass needle. Now, and what is the reason the compass needle aligned west to east? We have to think, because this compass needle will align in the direction of the total magnetic field. The compass needle. That means we have two magnetic fields now, BH and BC, and the B total is acting in this direction. This is the direction of resultant magnetic field, B total. That is why it is aligned in that direction. So how can you find it, that resultant direction? We have to complete a parallelogram here. So complete the parallelogram. Like this. Now the diagonal of the parallelogram gives the resultant magnetic field. Diagonal of the parallelogram gives the resultant magnetic field B total. And all these angles we know. This angle is 45 degree, next angle is also 45 degree, and here this angle is also 45 degree. 45 degree, and this side is BH, so here also it is BH, and here it forms a right angled triangle, and already we have seen this angle will be 45 degree. So in that angle we can calculate the value of sine 45. So we have sine 45 is equal to BH upon BC, opposite side by hypotenuse. From that equation, we will get the horizontal component of earth magnetic field. BH is equal to BC sine 45 is equal to value of BC is magnetic field at the center of a circular coil, mu naught by 4 pi 2 pi I n upon r into sine 45 will give you the value of BH. Next, second part of the question. The current in the coil is reversed. The coil is rotated about its vertical axis by the angle of 90 degree in the anti-clockwise sense, looking from above. predict the direction of the needle. Once again, we have north, south, east, west directions. Now, at present, we can see BH is acting towards north, and it remains in the same direction, BH towards north. And BC is acting in this direction. This is the condition before making the changes. Now, the current becomes opposite. Current becomes opposite means what happens? Now, BC becomes opposite. So, this will be the value of BC now. When the current opposite, magnetic field due to the coil becomes opposite. BC in the opposite direction, so that the previous direction of BC we can just change into dotted lines. Now it says that the coil rotates through an angle 90 degree in anti-clockwise direction. The coil is rotated through an angle 90 degree from here. So when the coil is rotated 90 degree, we know direction of BC also will be rotated. So then what happens? Now the BC, after rotating 90 degree, the BC will be in this direction. BC 45 plus 45, 90 degree. That means the older direction, once again, the older direction of BC we can make it as dotted line. So this is BC, BH. Now for this BC and BH, we have to complete the parallelogram. So like this. So that you can see what is the direction of the resultant now. The resultant magnetic field is acting in this direction. B total is acting in this direction now. Direction of B total. That means now just compare with the party A, direction of B total, and here direction of B total. It will be just opposite. Therefore, now if we place the needle, then what will happen to the needle? Again, assume that the needle is placed like this. Magnetic needle is placed. In such a situation, this will be north and this will be south. The needle will align just opposite to that. That means in the first case, we can see the needle. The first case needle points west to east. Now needle in the opposite direction. So we can say the needle will be in east to west direction. Needle is just opposite. That is east to west direction. Now, question 21. A magnetic dipole is under the influence of two magnetic fields. The angle between them, between the field directions is 60 degree, and one of the fields has a magnitude of 1.2 into 10 power minus 2 Tesla. If the dipole comes to stable equilibrium at an angle of 15 degree with this field, what is the magnitude of the other fields? So assume two magnetic fields. Say the magnetic field B1 and the second one, the magnetic field B2, and a magnetic needle is placed between these two fields like this. Magnetic needle is placed and needle is at equilibrium. And with the B1, the angle is 15 degree and the total angle is 60 degree, which means the remaining angle here with the B2 is total angle 60 degrees, so the remaining angle is 45 degree. Now, under what condition the needle is at equilibrium, we have to think the needle is at both the external fields will apply torque on the magnetic field. Needle is at equilibrium when torque applied with the first magnetic field is equal to the torque applied by the second magnetic field. That is, tau 1 is equal to tau 2. That is equal to mb1 sine theta 1. Sine theta 1 is 15. Is equal to mb2 sine 45. M is same because we have the same needle, same magnetic moment. From that, you can find the value of B2. B2 is equal to B1 sine 15 upon sine 45. Substituting the values, you will get the answer. Then, next, question 22. A monoenergetic 18 kilo electron volt is the energy. Electron beam initially in the horizontal direction is subjected to a horizontal magnetic field of 0.04 Tesla. I think you can take 0.4 Tesla. Then only you get the correct answer, I think. Not Tesla, sorry, Gauss. 0.4 Gauss. Normal to the initial direction. Estimate the up or down deflection of the beam over a distance of 30 centimeter. Also, electron is given. Okay. So here. A monoenergetic electron beam is traveling like this. The moment it reaches here, a magnetic field is applied. So naturally, in a magnetic field, a charge follows circular path. Now here, what happens? The charge now follows circular path, and what we have to calculate according to the question. So here, during that time, okay, it travels for 30 centimeter of arc length. The center of 30 centimeter of arc length. It goes. Now, by that time, how much deflection downward? Take this point P and this point Q. So what you have to find out? You have to find out the deflection downward. That is, the distance QP has to be calculated. Now, how can you calculate QP? That is what next we have to see. So here, this angle you can take theta. Okay, let's start now. First of all, we can take energy is equal to QV or EV. Then V capital B, 18 kilo electron volt. Kilo you have to convert into electron volt, then multiply by electronic charge, then you will get energy. Q is equal to E, electronic charge. And that energy is converted to kinetic energy, so half mv square. From that equation, you can find the value of velocity v. Velocity v is equal to under root 2q capital V upon m. So you will get first velocity. Once you get velocity, we know that VQV, again Q is equal to E. VQV, magnetic force will give the necessary centripetal force mv square by r. From this equation, you find the radius of the circular path followed by the particle, that is mv by v. Substitute the values, find the value of r. Once you get the value of r, we need to find qp. qp is equal to OQ minus OP. OQ minus OP. And OQ is nothing but radius r minus OP. What is OP? We want to find OP. We can use this right angle triangle. Now you will get OP is equal to suppose this point is capital R. OP is equal to OR cos theta is equal to R cos theta, because OR is the radius itself. So OP is equal to R minus R cos theta, that is equal to R into 1 minus cos theta. R into 1 minus cos theta. Now here theta we have to find. Theta is equal to, angle is equal to arc length 30. In meter you have to take 0.3 upon R. So you will get the value of theta. Assume angle is very small so that you can directly substitute there. So substitute the value of theta, then you will get the deflection Q. Then next, question 24, a Roland ring, or Roland ring means you can take it as a toroid. Roland ring of mean radius 15 centimeter has 3,500 turns of wire wound on a ferromagnetic core of relative permeability 800. What is the magnetic field B in the core for the magnetizing current of 1.2 ampere? Okay, so we have the formula. Magnetic field due to toroid with core material, we have mu naught mu r ni. Now here total number of turns only given, therefore you have to modify the equation mu naught mu r capital N upon 2 pi r, number of turns per unit length, into I. Substitute the given values, you will get the equation for magnetic field. Now question 25, the magnetic moment vectors mu s and mu l, okay, spin and angular moment, associated with the intrinsic spin angular moment s and orbital angular moment l respectively of an electron are predicted by quantum theory and verified experimentally to a high accuracy, okay, to be given by mu s is equal to minus em into s and mu l is equal to minus el by 2m. This mu l is equal to minus el by 2m we have already derived. Which of these relations in accordance with the result expected classically? Okay. So in classical explanation, actually we have done for mu l, which we have derived already. Okay. Magnetic moment of electron in the orbit, we got el by 2m. And here, but when we think about mu s, this much only you have to understand. Okay, mu s value is almost double than the expected value, because in mu l there is a 2 in denominator, but mu s you cannot see that 2. Therefore, mu s is getting almost double as expected. That's it. Okay, so these are the numerical problems from this chapter.